Am I being amplified? Okay. Thank you, Kevin. That was really good of you. I guess I would like to wax nostalgic just for a tiny instant here. As Kevin said, I got into linguistics at Harvard, and in fact, I got into linguistics when I was 18 years old and showed up here as a freshman. And indeed, if I remember correctly, the first college class I ever attended was Intro Linguistics. The teacher was Jay. And we're talking about four decades almost. And I have to tell you a little bit about the class. The room was quite a bit scruffier back then. This remodel is gorgeous. And outside, I think Seaver was kind of in bad shape because outside there was a guy with a jackhammer and making an appalling noise. Jay rose to the occasion by pacing back and forth, looking at the floor and muttering. But my hearing was really good back then because I was only 18. And I think it shows, you know, I was vaguely resentful at the murmuring and the jackhammer, but also kind of inwardly I was thinking, oh, cool. And I signed up for the linguistics major at the end of that semester, so I believe I can count as a convert. Oh, the last thing, yeah, it was this very room. So it's really kind of strange coincidence. Yeah, you wouldn't remember, right? Because you taught the course a million. Yeah, no, it was this room. Okay, so I better start giving the talk now before I wax maudlin, but here we go. Saltation in phonology. Let's start by defining it. It comes from the Latin root for leaping. And it occurs when one sound leaps over another. So to take an example from Campanian Sardinian, a work of Bolognese. In a certain context, roughly speaking, intervocalically, the sound P is realized as a beta, right? So it turns from a voiceless stop to a voiced fricative. In the very same context, B, which is a voiced stop and is therefore intermediate between P and beta, stays the same. So let's look at some data under 2. You all have handouts now? Yeah, okay. Look at 2 on your handout. The nice fish, belu plus pisci gives you beluici with that beta. Similarly for the T and K becoming ev and gamma, whereas subinu, the wine, the B stays the same, and likewise the D and the G stay the same. So the voiceless stops are saltating, leaping over the voice stops to arrive at the corresponding voiced fricatives, and that's going to be our central example here. This talk is something of a mix with various goals. An empirical, analytical, theoretical, experimental, etc. tour of the phenomenon. And let me just give you a quick overview before plunging in. I'm going to give you a few examples of saltation. The theme here is that saltation, as far as we know, always has peculiar historical origins. No language ever up and decided to have a saltatory alternation. They always come from strange directions. Second, I'll turn to mainstream phonological analysis, point out, following earlier literature, why classical optimality theory cannot handle saltation. I'll address another proposal in the literature due to Lubavitchs and suggest that it's not such a great idea as an analysis. And finally put forth the core of the talk, a new proposal based on Kai Zura's star map and Velko Stereati's P-map theory. Believe me, in rehearsal this fits in an hour. So psycholinguistics, saltation appears to be hard to learn. Experimental work by my student, James White. Computational work on learnability, attempting to find an explanation for why saltation is hard to learn. And finally, I'll sum up with some remarks about phonology in general, what we might be learning from all this. Okay, so that's the plan. Let's start with the travelogue. I'll give you a few cases of saltation. I only know of about 10 of them. They're hard to find. If you know more, kindly tell me. We keep looking for more, but it doesn't seem to be a common phenomenon. And as I mentioned just a minute ago, saltation, as far as we can tell, is always a restructured phenomenon. It is never a fresh sound change. It results from accidental combinations of circumstances. Indeed, both Lass and Minkova, historical linguists, suggest that there is no such thing as saltation, even from the viewpoint of the IPA chart, right? You cannot leap across some intermediate sound, even if it's a possible sound in other languages, from which, of course, it would follow as a logical consequence that no language can innovate a saltatory alternation. Okay, so let's start looking at other cases. The first historical origin of saltation that I know about is the consequence of borrowing. So let's do an example taken from Ito and Mester's work on Standard German. In Standard German, g saltates over k to become the voiceless palatal fricative h in the environment after an I word finally. So underlying König becomes König, and the underlying form can be justified by the alternating form Könige, kings. The words that have ich word finally in German are all patently cosmopolitan words, like plastik and batik. And electronic search indicates that this is true. There were no native German words that had ich in this position, and so it was the interposition of the Ks by borrowing that caused the g to h alternation to become saltatory. Similar cases, Slovak e o saltate over e and o to become je and o. E and o are borrowed phonemes in Slovak. Polish, g saltates over j in becoming j. The j items come from borrowed stems. All right, so that's a very simple origin for saltation. The next case, type 2, is rather more intricate and I think more interesting. It's a case where a language had A becoming C, and again, B is interposed, but this time the mechanism whereby it became interposed was change in the grammar. So let's see how this might have worked. The example is Campanian, which you heard at the beginning of the talk. Here is what we think is going on in the history of Campanian. It was originally not saltatory at all. Rather, it was a fairly standard Linician chain in which the P and the B were phonetically evolving in the direction of 0, gradually and in parallel, maintaining a distinction at all times. So we can conjecture that it all started out like in A at the bottom of page 2, Belupisci Sabiu. The P lenited to B while the B lenited to beta. And then came, this is conjecture, but I'll argue for it, the crisis stage is when the B from P lenited to beta, and the beta from B lenited all the way to 0. I'm calling this the crisis stage because it created a massive neutralization in stem initial position. All of B, D, and G, and of course the vowel stems, neutralized to become vowel stems in this context. This seems to have been intolerable, and it triggered a massive restructuring of the system. The restructuring consisted of taking the isolation form and restoring it to the phrasal position. So in the post-crisis stage, after a new generation of speakers is restructured, we have modern Campanian, Beluvici and Subino. That make sense? Okay, that's the scheme. Now, why should we think this is true? Here are the reasons. There are neighboring dialects of Sardinian in which the hypothesized intermediate stage B goes to beta between vowels is still preserved to this day. Second, and more importantly, even in modern Campanian, you can observe these historical relics. Here's how they work. A certain limited inventory of words actually still has B0 alternation. So a word like bia, meaning road, you can either say sabia or you can say saia. Now, what's going on here? There's two interesting observations that Bolognese makes. One is that the use of the zero form does not occur in rapid fluent speech as you would expect for lenition. It occurs in careful speech. So that in itself is kind of a puzzle. In addition, the eligible words, if you go through his book, it seems pretty clear that the eligible words for this alternation are common words of the core vocabulary. Words like, if you look at the footnote, of, want, road, house. Non-alternating words are fancier words like doctor, drill, rubber, chicory, and so on. So what's happening here? I think the right line to take is that this is allomorphy. A certain restricted number of words are memorized as having two allomorphs, and when you're being more careful and can retrieve the unusual zero allomorph, you call it forth from memory and use it. At any rate, these are the evidence. As always, of course, in historical linguistics, relic forms tell you the earlier state of the language, which clearly had deletion of these sounds. The upshot then is in 8, saltation was not a sound change in Campanian. Rather, the B was interposed along the path due to the loss of productive alternation of B0. Okay, that's 2 of the cases. There's one more. And I risk being mean to a friend by calling it hypercorrection, but that's what I'm going to call it. It occurs in North German and is documented by Ito and Mester, and further information on the history from Ziemunski, Robinson, and Pilch. Let me give you just schematically the way that this system evolved historically. And I'm just going to give you words that I remembered from my Harvard College German. They aren't actual data, but they're schematic forms. The system evolved like this. First, you had simple G stems, K stems, and H stems. Fragen, frag, dicke, dick, machen, mach. The G's spirantized after vowels, so now we have fragen, frag, and again, the other two unchanged. Put in the well-known final devoicing, and we now have fragen, frag, and the others continue to remain the same. This is a variety that's described in my sources as vernacular North German, right? Widely used by ordinary people. The sources also describe a so-called refined North German. Okay, so what does it mean to be refined? Well, this is not the totally standard television German. That German doesn't have gammas. It has g across the board. What seems to be happening is that the speakers are converting their gammas, it's a simple allophonic change, to g. But once they've done that, it now saltates across k in turning into ch. The proof of this is that individual speakers actually can produce both varieties in different speaking styles. So Armin Mester indicated to me that when speaking with friends and family at home, he uses the gamma and is therefore not saltatory, but in sort of public context, he uses the g and is saltatory. So the little arrow diagram shows you what happened. G to gamma by sound change, evolving to h, finally, hypercorrecting back to g, and once you have that, you have your saltation. So let's sum up. That's the travelogue, end of, you may turn off the slide projector, castles on the Rhine and so on. The empirical picture is this. Cases are not abundant, which we might expect if the only way that they can arise is through these strange historical accidents. I'll suggest later on in the talk that saltation is hard to learn. It's possible, but very difficult to prove, that that may also have some role in the rarity of the phenomenon. Okay, clear so far? That's the data. Let's turn to analysis. Let me bring optimality theory onto the scene. I do most of my work in optimality theory and think it's a tremendously useful research tool. I say that because the handout continues. This is the theory that is famous for needing to be repaired. When it appeared on the scene, everybody, absolutely everybody, said, "What are you going to do about opacity?" And there have now been a huge number of proposed solutions for repairing the theory. There's just very, very large literature on the topic, which I'll return to at the end of the talk. Much less famous is saltation as problematic for classical optimality theory. And this problematic status was pointed out by Anya Lubavitch and endorsed by Ito and Nestor. So let me talk about their work for a minute. First, the simple argument that classical OT will not work for saltation. Let's analyze Campanian in the classical framework. We'll need some markedness constraints. So a ban on intervocalic voiceless sounds, a ban on intervocalic stops, that's the minus continuant. Next page, we need some faithfulness constraints. Ident voice favors retention of basic voicing. Ident continuant favors retention of basic stops. And if you go through the basic technique of the theory, you will find that P can become beta, as it does, only if each of those two markedness constraints dominates its opposing faithfulness constraint. So you need the arrows shown in the first tableau in page 5. But if you've got those arrows, you're stuck because the B is going to turn into beta as well. And that's what the second tableau shows. So the theory doesn't work for Campanian, and it's easy to generalize these basic arguments and show that it's not going to work for any other case of saltation as well. All right. Oh, so what to do? Lubavitch came up with a really ingenious solution, which I will summarize and then criticize. What she put forth as the way of getting saltation is a form of constraint conjunction. Constraint conjunction is when you take two constraints, put them together, connect them with logical and stipulate that they have to be applying in the same spot in the word for there to be a violation of the conjoined constraint. The idea from Smolensky has a decent pedigree. For instance, it does nice work in conjoining markedness constraints. Taking Ito and Mester's example, it's generally bad in languages for obstruents to be voiced. It's bad for consonants to be in coda position. And it is especially bad to be a voiced obstruent coda, as for instance in German. And you could get that with a conjoined constraint, as shown. Lubavitch had a slightly braver idea, which is to conjoin markedness with faithfulness. So it's a novel constraint type. Let's take her Campanian analysis. What you conjoin is ident voice and the ban on intervocalic stops. This is, don't simultaneously be unfaithful to voicing and be an intervocalic stop. In the tableau on page 6, you can see a sketch of how this would work. The crucial conjoined constraint is at the beginning, highest ranked in the first tableau. It rules out ABBA as a candidate for underlying APA. And in fact, if you look at this tableau and do the standard scansion by eye, you will see that if we didn't have that in the grammar, the winner would in fact be ABBA, which would be wrong. Okay, so that's the constraint doing its job. The constraint doesn't apply to underlying ABBA because you're already faithful to voice, and it's quite straightforward to get ABBA to be the winner for underlying ABBA. And this generalizes. You can apply this analytic strategy to all of the cases, and it works fine. Okay. The criticism is not of its this story as an account of saltation per se. Rather, it's kind of a loaded weapon that goes off in unwanted locations, producing disastrous predictions. So let me go through that. And I have to say, I learned this in an oral communication from Colin Wilson, who first pointed this out to me. Let us derive the following language. A language in which voiced obstruents are generally illegal, but they're okay just in case they occur in a triple consonant cluster. Okay, that's what we're going to derive. To do it, we will introduce a constraint which I will call the devil's constraint because it's doing wicked things. Ident voice conjoined with a star triple cluster. Now, let's imagine a language that is like Hawaiian, almost like Hawaiian, in that it has essentially no voiced obstruents. And of course, the standard OT ranking for that is star voiced obstruent outranks ident voice, and that will filter out any voiced obstruents that you might have been so foolish as to put into underlying forms. But in our version of Hawaiian, we're going to have the devil's constraint, and we will rank it on top. Let us see what happens. First of all, the simple case. If there were a ba, we want it to show up as pa, the standard so-called rich base strategy of OT. And if you look at the tableau and interpret it in the standard way, that's exactly what you're going to get. So ba is impossible. It gets fixed to something else. But now look at page 7. Here we have an underlying form that I will carefully pronounce for you, atbka. All right. Now, what's going to happen with atbka? Well, the candidate that might be sensible to be the winner would be that one at the end of the tableau, atbka. But observe, it has a triple cluster and in the same location is unfaithful to voicing. That candidate loses. The sensible one loses. What wins? Well, in fact, the winner turns out to be the faithful candidate. So it's atbka that emerges. Prediction: there ought to be languages out there in which there are voiced obstruents, but only within triple clusters. Anybody? Okay, I can ask, unless there were a malevolent person here who lied, I can ask that confidently, because this is not only unattested, but it seems just extremely unlikely. The idea that a marked thing suddenly becomes okay because it's in an overlapping marked context is just absurd. If anything, we would expect the opposite. Right? Okay. All right, so that seems to be what's wrong with that analysis. And I suspect that the right way to go is to forbid this kind of constraint and look for some other story for how it's going to work. So here's the proposal, and this is sort of the proposal of this talk. What do we want the theory to look like? Well, certainly we have to expand the power of classical OT in order to get saltation, but we want to avoid this severe collateral damage. And for reasons that I'll give in a little while, we think the theory ought to mildly discourage saltation, to make it kind of a marked phenomenon. Okay, how are we going to do it? Step 1, abandon the minimality restriction, as we'll call it, on classical OT, in classical OT on faithfulness constraints. In correspondence theory, McCarthy Prince 95, which laid out the completely standard theory of correspondence constraints, when they were setting up their system, they quite sensibly adopted an atomistic approach. Let's just have one faithfulness constraint for each individual feature, the simplest possible theory. And whenever we have candidates that change more than one feature, well, that's just more than one constraint. Okay. Kai Zura, in a 2007 paper in Language, suggested that there might be reasons to permit supraminimal faithfulness constraints. That is, they ban differences that are more than the sheer minimum. That's the first part of the proposal. But the other part, which is also crucial, is that we impose a kind of penalty on their supraminimal status. So let's take a look. The format of the constraint is star map in 20. Star map xy assesses a violation to a candidate if a segment belonging to natural class X in the input is mapped to a corresponding segment in natural class Y in the output. Now, how does the penalty work? The penalty is based on phonetic substance, all right? Star map constraints are assigned a default ranking, a natural ranking in the grammar, in the way given in the arrow in 21. Those star map constraints that ban changes that cover a larger perceptual distance are assigned a default ranking that is higher than constraints banning smaller changes. This is taken to be a learning bias in universal grammar. The language learner approaching the ambient language expects the constraints to be ranked this way and needs extra data and persuasion to override this expectation. Okay. Given some huge pile of data, they will override it and thus become little Campanian speakers. But it's a default expectation. A little bit more on the theory. Where do these similarity relations come from? Well, these are taken to come from Doncasteriades' idea of the P-map. This is an extensive compilation of the language learner's phonetic experience concerning the perceptual distance between forms of the language. So the assumption here is that in arriving at the default ranking of star map constraints, the language learner consults her P-map. One last bit of background. The idea here, though recently implemented, is actually quite an old one. What it translates to in the empirical domain is that we expect phonological alternation to be phonetically minimal. And that is an idea that, in fact, goes back a long way, certainly into the 70s with work by Veneman and Koparski, and I'm sure into earlier decades if people with better scholarship than me could find them. I tried. I was steered to something by Wilhelm von Humboldt, which I couldn't interpret at all, so it's not in the handout. Okay, empirically speaking, I think there's quite a bit of evidence that this is true, both from Koparski's classical studies of language change that he did in the 60s and 70s, and then various empirical studies of phenomena like reduplication, rhyming, puns, infixation, artificial language learning, and so on. Okay. So what's new here, in this century at least, is the formal apparatus to formalize a preference, to formalize a bias, and a way to test it empirically. And that's what I'll be talking about here. First, let's just make sure that it works for Campanian. Here's the analysis. There's a star map constraint banning P beta alternation. There's one banning B beta alternation, where P and beta stand for whole classes across places of articulation. The rankings that you need, star B beta dominates star intervocalic stop to keep B from spirantizing. Star intervocalic stop dominates star map P beta because P does spirantize. And of course, by transitivity, we'll get the ranking star map B beta dominates star map P beta. This I will refer to as non-P-map compliant. It is an unnatural ranking. And of course, the reason is that B is patently closer to beta than P is. This is a disfavored grammar in a sense that I'll make explicit later on. For now, just to reassure ourselves that the analysis works, I give you little tiny tableaus. The APA does indeed become ABA as we want. And on the next page, the ABA is stable as we want. And as before, the result generalizes to get any case of saltation in which A becomes C leaping over B. The ranking that you need is star map for BC, dominating the markedness constraint that compels the change, dominating star map AC, hence a non-P-map compliant ranking. Okay, now, I've told you that this is a marked phenomenon, but I haven't given you much evidence that this is true. You might take it as a little weak argument that saltation seems to be rare and has a peculiar historical origin. But I think much more persuasive evidence can be obtained if you directly intervene to obtain the testimony. And this involves learnability. The way that the dispreference for saltation, or more precisely, for non-P-map compliant rankings, can be tested is to make people learn a novel language that has exactly these properties. Indeed, say, a language that is artificial but looks a lot like Campanian. So that's going to be the scheme. So I'm going to report an artificial language learning study done by James White, who I will henceforth refer to as Jamie, who's a grad student at UCLA, writing a dissertation under partly my supervision. And it's going to come out soon. Jamie is coming east to Ottawa, so take him under your wing and talk to him. All right. So here's the experiment. This is, I'm not going to give you the details, just sort of the essence of the experiment. It's really Jamie's job to tie up all the ribbons properly. But you go into the lab, and a computer is in front of you, and you see a pretty red picture of a strawberry and a voice that says to you, "Come up," and you're supposed to learn it. And then you see two pretty red strawberries, and the voice says, "Kamavi," where the V is an English acceptable equivalent of Campanian beta. It's not just P and B and V. There's analogous stimuli with T, D, and EV, but I'll only talk about PB beta. Let's go through some experiments. Experiment 1. Train the subjects with a bunch of forms that have PV alternations, like the one I just described, so that they don't catch on consciously. Make sure that there's plenty of filler forms that do not change with things like sonorants and fricatives. And then, once they've spent, say, 40 minutes learning the artificial language, you can test their knowledge with either the words they've already heard before or new ones. So the way the testing works is always 2 alternative force choice. So you see a nice turtle. Maybe you haven't heard tinap before, but now you must guess. Are the 3 turtles tinapi or tinabi? All right. Now, Jamie uses only data from people who did a good job of learning the language in the first place. So if they didn't get 80% or better on the train words, he just throws their data out because they just weren't learning well enough. You want to get the data from the people who did learn it and then see how they generalize. Okay, now comes the essential thing. B and F did not occur at the end of stems in the experiment, but you can test them on new B stems like talab or F stems like timaf. What do they do? Well, let's look at some results. First of all, the people tended to get the PV alternation pretty accurately. Okay, so they could learn the language, at least insofar as it involved imitating what they had directly heard. Moreover, they were quite good at not applying any rule to those filler consonants like the nasals and the fricatives and so on. But what about B and F? As it turns out, these are frequently changed to V. You can see the percentages in the diagram, bottom of page 10. Right? Now, this in itself should not persuade you, because there's an alternative explanation. This could be due simply to rule generalization. Okay? If you just hear P to V, that's compatible with quite a few hypotheses. It might be a very specific rule taking P to V, which is indeed the first rule on page 11, but it might be a more general rule applying to all of the sonorants. And if that's the rule, then B and F would turn into V as well. The data are compatible with both. So there has to be a control experiment, and that's experiment 2. This time around, train on B to V, not saltatory, with the same fillers. Saltation is not at stake, but generalization is. So how did it come out? And in fact, here's the essential result. In 34, the bold arrow is trained and tested. The dotted arrows are tested only. Experiment 1, potentially saltatory, massive generalization. Experiment 2, the control, not potentially saltatory, only modest generalization. Well, what's the interpretation? It seems that there are both generalization and saltation effects. It's the saltation effect that matters here, right? And that's the conclusion in bold italics. If the interpretation of the experiment is correct, subjects are reluctant to posit that an alternation is saltatory. One other experiment that actually nails it down rather nicely. Experiment 3 is just like experiment 1, but this time you give them B stems that do not alternate, right? So they are getting talab, talabi, all right? Despite getting these stems, they frequently blunder. They turn the B into V anyway, even though they got evidence that you shouldn't do it. Okay, so that's, and again, there's a control experiment suggesting the cause is dislike for saltation rather than generalization. All right, that's the empirical evidence for the markedness of saltation. Let me return once more to theory for trying to make a little bit more sense of this evidence. We're saying saltation is bad. Learners are biased against it. And that's fine, but it's a very intuitive idea. Can we make an explicit theory that will pin these notions down? And can the theory be made to work? And that's sort of the last main topic we'll talk about here. Bias means, in this context, downgraded for consideration during language acquisition. Jamie White's experiments suggest that the language learners find saltation a priori unlikely. We certainly want the theory to impose a bias and not an outright prohibition, because little Campanian children quite plainly do learn the system. Of course, they get much more data than 1 hour. And in fact, Bolognese rather carefully documents the productivity of the alternation in Campanian. So what kind of theory could give us, give substance to the idea of a learning bias? And we turn here to work by Colin Wilson that provides the apparatus that we need. Wilson first put forth these ideas in his efforts to model another artificial language experiment that he did involving palatalization of velars before high and front vowels. But here I'm going to talk not about that experiment, but the tools that Wilson put forth for doing this kind of work. What you need are 2 things: a slightly different constraint-based framework for phonology, and you need some results in computational learning theory. Let's go through these. The different phonological framework is Maxent grammars, first introduced, as far as I know, by Goldwater and Johnson. It's an awful lot like OT. You're going to have gen creating candidates. You're going to have an eval component picking winners. But the eval, instead of being based on constraint ranking, is based on a little bit of math. Every constraint gets a weight. It's a non-negative real number, and it represents the strength of the constraint. There is a formula given in the footnote that takes the weights and the violations and uses them to calculate a probability for every output candidate. And of course, this is just what you want for modeling a case like Jamie White's experiments, because we're getting free variation in the output forms. We want to model the actual percentages with which they were created by the subjects. Next, we have to say something about learning. As with other constraint-based frameworks, Maxent grammars come with research on the learnability question: what algorithms could discover the right weights for the constraints? The results of this research, alas not by linguists, but by computer scientists, are extremely gratifying. Given a set of quantitative data with constraints, with their violations, there is indeed a unique grammar assignment of weights that best fits the data. Moreover, there are many algorithms that are guaranteed to find these weights under all circumstances, and these algorithms are typically very fast. So if you've worked in other constraint-based frameworks, it's a lot harder. So, okay. That's the first nice bit. The second nice bit is, what about these learning biases? What about SoftUG? It is feasible in this system to begin the learning process with a bias placed on every constraint. A commonly used bias, the Gaussian prior, is based on 2 numbers. Here we go. Mu is the preferred weight of the constraint. Sigma expresses how much the constraint is willing to diverge from its preferred weight. Okay. So what about here, moving towards the modeling that we'll be doing? Where do our sigmas and mu's come from? The sigmas are, as in Wilson's work, an implementation of PMAP theory. From the perceptual closeness of sounds X and Y, measurable in an experiment, we deduce, by means I'll tell you about, the mu, the preferred weight of star map XY. What about sigma? Well, here an ad hoc choice was made. White set it at 0.5. This is a value that allows the mu's to have a substantial but not overwhelming effect. Okay, now let's start doing White's application of these ideas. First step is to get our mu values. He got them empirically by taking an old perceptual confusion and noise experiment by Wang and Bilger and writing a little Maxent grammar that predicted the frequencies of errors. The resulting weights were used as the values for mu, and you can see them on page 14. In fact, I think these are intuitive. Notice that star map BV is at 0, and even for English speakers, and certainly for speakers of many other languages, B and V are very, very close. It's P and V of the labials that are furthest apart, and notice that huge weight for sonorants and obstruents. The mu's for markedness constraints were set at 0 by fiat. Okay, so now we can start modeling. Take these mu's and sigmas, take the constraints given earlier, and give the computational model exactly the same training that the experimental training data that the experimental subjects got. Okay, so you let it pretend to be a subject. You do a separate simulation for each experiment because each experiment is a different pretend language. All right. So in other words, we're trying to mimic people. 44 shows how the weights were changed during the learning for the artificial language of experiment 3. This is the language where P becomes V, but B stays the same. During training, the weights changed as shown in 44. The ones I want you to notice in particular, though, are that star map went down from its mu value to 1.04. Why is it descending? Well, it's being bombarded with data in which P becomes V. Star map BV, starting at 0, went up to 1.51. Why did it rise? Well, it's being bombarded with data saying that B does not change. So that's the intuitive basis for what the math is doing. So what is the bias doing here? To clarify this, I took the same input file just for presentational purposes, and I ran it without the bias. So what happens then? Well, without bias, star map PV gets a 0 weight. That evidence that it ought to be weighted low has its full effect demoting it to 0. Without a bias, star map BV gets an extremely high weight because the data is saying you should have a high weight and there's no bias present. Okay. So that's how learning works under the model, biased learning. The last step is sort of the empirical payoff. Take these learned grammars and give them this time the test forms that were given to the experimental subjects. And now we can compare frequencies. Frequencies with which particular choices were made by the experimental subjects versus were made by the grammars that were learned. In general, the fit is pretty good, and I want to give you just 2 sample results and a summary. 47, in experiment 3, if you train it on P goes to V, B stays the same. The people guessed counterfactually about 20% of the time that B should turn to V, and the model did exactly the same thing. Okay, why so? Because star map with a prior weight of 0 failed to rise high enough during learning to block this change. Second result, if at some point at your leisure you want to flip back to 31, you will find a curious asymmetry. The subjects offered F goes to V 45% of the time in experiment 1, B to V 70% of the time. Why so? Well, here's the chain of reasoning. Go back to Wang and Bilger's perceptual data. B is closer to V than F is to V. So when you calculate the μ's, star map FV is higher than star map BV. So when you do the learning simulation, star map FV stays relatively high, so the model predicts that F is less likely to alternate. Overall, taking all observed percentages and all predicted percentages, you get the scattergram in 49 with a nice correlation. R is 0.95. So that's the basic story I want to tell. Let me conclude with the propaganda, very gentle, diffident propaganda. First, the prospects for SoftUG. I suspect that a lot of linguists have been wanting there to be SoftUG principles for a long time. There are an awful lot of tendencies, strong tendencies out there in language that nevertheless have exceptions here and there. But the problem with SoftUG is the sense of rigor. How do we take SoftUG and make it into a rigorous theory? The possible answer seen in this talk is SoftUG is embodied as a learning bias using the μ's. And the right formal language to do this is Maxent. As far as empirically assessing such biases, experiments on artificial languages provide data about learning difficulty that might be hard to obtain in the wild, where the learners have so much time available to learn even difficult patterns. The second bit of sort of more general discussion here concerns the goals of phonological theory. I can see at least two goals. One of these is the really obvious goal. If you do phonology, you go out and study languages and you find these beautifully intricate, complicated systems. We want the theoretical tools whereby we can analyze these systems and understand them. That goes without saying. Rather more subtly, though, you could take it as a goal for phonological theory that it should make correct predictions about what is hard for people. Okay? What are the cases in which language acquisition is liable to fail? And in this talk, I've given you two examples. One was Jamie White's experiments. The second, go back to the early part of the talk, where I suggested that modern Campbellian is itself the result of a drastic error made by young Campbellian children at some point in time. So these things happen. Predicting what is hard for language learners is certainly not a new research goal in generative phonology. If you go back to the classic work of Koparski that he did in the 60s through early 80s, he was trying to explain exactly this. He was looking at cases where acquisition fails and languages change, and he was trying to predict the circumstances under which this would occur. In fact, it's sort of astonishing. I went back to read his compiled book where he says pretty much exactly what I wanted to say in this talk, whatever it is, 43 years ago. Okay. So, keeping this research goal in mind, let me go back to something I mentioned very early in the talk, namely the question of remedies for opacity, right? All the people trying to fix classical OT. There's a relatively new theory on the market put forth by John McCarthy and his colleagues that I swear is the best theory of phonological opacity that has ever been invented. It is a tour de force. No question about it. As far as I can tell, every classical opaque system of the kind that we give to our students in phonology problem sets has a strikingly elegant analysis under this theory. And I suspect that the basis for these analyses is very often close recapitulation of diachrony. The derivations in the system will very frequently look like the history of the language in question. The question that I want to definitely put forth is this exactly what we want? In the development of this wonderfully virtuosic theory, has Koparski's original motivation for discussing opacity, he invented the term, been forgotten? I swear, Koparski was not trying to invent a disease that would affect a future invented theory. He was using opacity as a tool to understand cases of language breakdown and change. And I think that still ought to be part of our research focus. In this connection, I would like to put forth a suggestion that quite a few of the classical problem sets are deceptive. That if you do the problem set and solve it in the framework, it will make you very, very happy. But if you dig through the literature, often a little bit less prominent literature, you'll find people who've taken a closer look at the language in question. And my little collection of cases is given in small print in 53. A lot of these cases have had serious changes that don't fit the standard analysis. Some of them have had extremely drastic changes indicating total breakdown. Okay? So the Koparskian criterion is indeed present for quite a few of the most prominent cases that have been put forth as cases in the study of opacity. So that's the scheme. These may be problematic for a theory in which opacity seems to flow as smooth as oil. The theory is perhaps too good. So what I would like to see, and would love to have given you a beautiful, beautiful talk that completely solved, what's the theory of opacity that properly characterizes the stable cases, because I think there are stable cases, but also identifies the cases that are eligible for breakdown. Just making a few guesses, if you keep that Campadanian example in mind, I believe that the key to the stability of opacity is the global similarity relations that are found among overt forms in the paradigm, rather than the very local similarity relations that governed how the paradigm was historically created and which indeed dominate the derivations of these forms in harmonic serialism. Okay, that's the spiel. So summing up the talk as a whole, saltation is a minor topic in phonology in terms of its empirical scope, but it is perhaps informative concerning the usefulness of theoretical approaches to phonology. The cases that strike me as possible winners here are appeal to phonetic substance in the form of star map, cum, pmap for explanation, gradient versions of UG expressed as learning biases, and finally, fuzzy theories made rigorous through the use of appropriate experiments. Thank you.